This is Lab 5, and it'll be hosted by me, Sri Harsha, and Ahmed Alasan, who's joining online. Cool. So I'll give you a quick rundown of what we're going to do today. So as you can see on the board, we're going to have a quick rundown of basic CNN components, essentially from the dataset to the actual architecture and then the classes that we'll use. Then we'll spend some time getting our hands dirty with some actual PyTorch code, going over important functions.
Hi, good morning.
That will be used.
Thanks for joining me
And
here.
slowly work
Today's
our way
gonna
through
be the lab
checkpoints
on
that
CNN
will help us
basics and
understand the
backdrop.
overall model flow and the workflow when you're using a CNN to solve a problem. We'll have extensive focus on the special PyTorch operators that are maybe unique to CNNs, but some of which you may have seen before. Then at the end, after we're done with the checkpoints, I'll happily take questions about implementation. I'd like you guys to respond to the Piazza poll as and when you complete those checkpoints. And ultimately, today's session is not really going to be teaching about CNNs, but rather how to implement them, more so the coding part. But I'm obviously happy to answer any doubts you might have after the conclusion of the session. So overall, these are the checkpoints that we'll be following. As I said, we'll start with some basic data loading, data preprocessing. Then, as is important with any deep learning task, we'll have a little bit of exploratory data analysis that basically takes a look at our data set, understands the class distributions, and in the case of images, visualizes a few images to understand how much noise is there in the images, are objects centered in the image or are they to the side, and whatnot. Then we'll build a CNN model, and as with PyTorch, which is the language we'll be using today, we'll define a loss and an optimizer. You must have seen these in Homework 1, Part 2. Then we'll train the model, evaluate the model, visualize intermediate feature maps. This is maybe something more unique to CNNs because you can actually see a visual output rather than a string of characters, which is what an MLP really is. We'll visualize some of these features, these learned convolutional kernels, and then we'll have a conclusion, and I'm happy to discuss anything you might want to talk about regarding CNNs. All right, so basic introduction to the dataset we'll be using. We'll be using the CFAR10 dataset. This is a very popular beginner dataset for convolutional neural networks. The 10 comes from the 10 classes that are used, as you see here, from airplane all the way till truck. And there's 60,000 total images, and it's split to 50,000 training test images and 10,000 test images. And even within those train and test images, there's a balanced class distribution. So what that means is there's 10% of each data class in this data set. So 5,000 airplane, 5,000 automobile, so on and so forth for the training data set. All these images are of size 3 cross 32 cross 32. That's rather small, but it helps us give a good enough example as to how CNNs work. The three, as you may have guessed, are the R, G, and B channels. So PyTorch actually helps us download and load this data set. So we'll be using this functionality that's torchvision.datasets.cfar10 to get started with. And in fact, this would bring us on to the first checkpoint in the notebook. I hope you guys have the latest notebook. You can try using torchvisions.datasets.cfar10 to load that. I will present that notebook as well. Okay, so I hope it's pretty clear that we have to fill in the train and test dataset part. And looking at the documentation for torch vision.datasets, ImageNet's another famous vision dataset. We just need to pass in the path to our dataset and then give a batch size, shuffle, num workers. You know the drill by this point. We can also quickly walk through the convolve2D function. Uh, Maybe we'll come to it later, but these are basically some functions that you'll need to write. Or, yeah, so for example, padding your image, because if you don't want to reduce the dimension of your output image, you usually do zero padding, but there are other methods for padding. You can repeat the last element, or you can warp the image around. So essentially, the element that's at the rightmost part of the image, you can then use it to pad the leftmost part of the image. And naturally, there's some math involved that combines the padding, the stride, and the convolutional kernel size that helps us understand the resultant output image size. Usually, kernels are odd in dimension, so it's usually 3 cross 3, 5 cross 5, 7 cross 7. But for this example, we're using a 2 cross 3. So this is data loading. I'll quickly add my solution as well, and we'll proceed forward. All right, so as you can see, Torch Vision allows us to download the dataset onto our Google Drive. I've created a train and test split, so that's easily specified by doing train equals true. Download is true because I don't have this locally. And naturally, because we're going to be dealing with tensors, the only transform we apply to start with is transforms.toTensor. I hope all of you got this. So now that we've loaded our data, what are we going to do with it? How are we going to process it? So for that, we're going to create our very own convolutional neural network. This is broadly what the structure looks like. Let's not get too intimidated by what individual functionality is. But yeah, as you can see, you start with an input image. Then you slide across the image your kernel, which is a set of parameters that we learn through backpropagation that defines our convolutional neural network. We have a convolution step plus ReLU. ReLUs are activation. Then comes something called pooling. You guys might be familiar, but we'll cover that as well. We do multiple steps that create feature maps at every interval. So once we slide a set of filters over an input, we get what we know as feature maps. So on repetition of applying convolutional kernels, you can see that our channel width increases. That's basically the amount of features that we now have through doing this convolutional operator. Finally, we always want to pass it to an MLP for a classification task. So CFAR10, as I said, it has 10 object image categories, so we're going to do some form of classification. However, we can't really apply an MLP directly to our 2D image. So what we do there is we then flatten it. We can use something like torch.tensor.view or flatten to get a resultant 1D array. Then we have several feed-forward network layers, which perform exactly the task of a normal MLP that result in an output layer where we'll have the output number of neurons equal to the number of classes that we have. Naturally, this output layer will have a softmax activation function. The reason being that softmax gives us output probabilities. And we cannot understand network logits, which are usually the outputs of the final layer of your MLP, but they're not normalized. So we don't really understand what they mean. But once we apply the softmax, they're easily understood probabilities for us. All right, so this is the PyTorch documentation for Conv2D. I hope you guys will be able to open that up locally as well. Uh, yeah. All right, before we get to that, let's talk about some transforms again that we will apply to our network. So here we saw that we were able to download the data set, but usually before we actually do any image processing, we want to apply basic transformations to our input data so that it's either easier for our network to learn, or in addition to normal transformations, we can do data augmentation, essentially rotating an image, flipping it, changing its color scale. This allows us to generate more data for free because we're basically just doing creating a transformed version of the data, but the labels for the data remain the same. So let's take a look at what we're going to do here. Now, as we saw earlier, we wanted to do .2 tensor, but another popular method of transformation for images is normalizing the image. Yeah, essentially we try to make it a zero mean unit variance sort of normalized distribution before passing it to the network. We want to do this for all of our trained data set and test data set. It doesn't make sense to apply a transformation just to the trained data set and not the test data set, because then it's like the input, also the convolutional neural network is seeing two different inputs. So let's go ahead and do that. Hey, I hope you two are following on. Like, are you guys fine? Like, we missed the initial few slides, but is everything okay?
Oh yeah, we went to the starting point.
Awesome. Okay, so essentially what we've done here is we've just created a list of transforms that will be applied sequentially to our data set. So first, we'll be doing torch.2 tensor, then we'll be normalizing our input data. Whoops. Sorry, it's transforms. Cool. It's always helpful to look at documentation when you're doing this. There's usually examples right at the bottom as well that help us understand, or it's almost usually plug and play syntax. All right, now we talk about data exploration. So as I said in the introduction, it's important for us to understand the sort of data that we're actually playing with, looking at the class distribution and looking at the images themselves to see if there's any need for specific processing. Say some images are too bright. That makes sense to normalize images across all your batches. So yeah, let's go ahead and run this out. Cool. So what we're doing here essentially is we're taking a range, we're creating a visualization plot. Yeah, matplotlib naturally expects height, comma width, comma channels rather than channels, comma height, comma width, which is what we're usually passing into our neural network. Then we're denormalizing for visualization. Remember we applied transforms dot normalize. So we're basically unnormalizing that, and then we're visualizing them and with their respective class labels. we're getting all of this from iterating through our trained data set. We can similarly do something for the test data set, but we'll expect to see something similar here. So here we can see that there are RGB images, albeit very pixelated. And one observation we can make right now is that the object that we're trying to classify sort of clearly stands out from the background, and it's usually centered in the image. This makes it easy for training. That's why CIFAR 10 is a good beginner data set. All right, yeah, now we're going to go ahead and build our CNN. So for that, I'd like us to take a moment to open up the Convolution 2D documentation on our laptops and just understand what exactly this formula here means. This star operator here is the convolution. You can think of it as sliding across our convolution kernel, across our image, across every row and every column, and then taking a resultant output that we call our feature map. We'll come back to what these inputs to the function are, but essentially this is a convolution operator. As you can see, we're sliding across one kernel, across our image, and it's important to note that here we have, what is it now, 7 cross 7 image. However, these outputs are 5 cross 5. So why does this happen? Essentially, it's because we're losing pixels because of how large our convolution kernel actually is. We can see that the center of the convolution kernel never actually starts from the top left or goes to the top right, or starts at the bottom left or goes to the bottom right. That results in a loss of some pixels towards the in the feature map. And ideally, I'd have encouraged you guys to understand or to come up with a formulation for what the output dimension should have been, given that it's a function of the padding. As I mentioned, we can like zero pad the image or warp the image for padding. Dilation, that's again something to do with the convolution kernel. We won't get into it now. You might cover it in class. And the kernel size. So while it might look a little complex, that this is the output dimension is a function of multiple things, in the documentation it's pretty clear. If you apply this formula, and this stands for the floor of the value you've computed, you'll know the resultant feature map size at the end. This is especially important when we're finally converting from a feature map to our linear layer. We need to know exactly what the input feature dimension is when we're writing our nn.linear layers in PyTorch. All right, cool. So I hope this is clear and you guys have opened up the documentation locally. We can go ahead and try to finish the next checkpoint. Oh, okay. I'll cover pooling operations as well, because that's also there in our to-do.
Excuse me.
Of course, yeah.
Uh, where can we find the slides for this lab?
I have not uploaded them, but I will check and maybe upload them up right after this recitation. I hope that's
Cool.
okay.
Okay. Yeah.
Cool. Before we get into pooling, are there any questions, like in person or online? I'll be happy to take them. I'll check the Zoom chat. Please give me a moment. All right, let's go ahead then. Yeah, so pooling. Pooling is a method of downsampling our feature map size or our image size. Usually it helps in removing noise from an image. Basically, there might be some pixels that have a higher value or a significantly lower value compared to what the image is actually meant to capture. So doing some form of max pooling or average pooling, you can think of denoises our image. Also, it helps reduce the final feature map size which is helpful when we talk about the parameter count or how heavy our neural network is. So the two main popular types of pooling, one is max pooling and the other is average pooling. The max pooling again slides across a kernel, slides a kernel across our image and takes the maximum value within that kernel. So in this example here, 5209, we get 9. 3023, naturally the answer is 3. That's what we see here. Similarly, we have, I hope everyone understands exactly what these dimensions mean. A kernel of size 2 cross 2, as we see here, and stride 2, because once we slide the kernel across this window of 2 cross 2, we're going to another new 2 cross 2 window without any overlap. That's essentially the stride of our kernel. Cool. Another popular method is average pooling, which essentially takes the sum and divides by the number of elements within that kernel. I think usually max pooling is used in practice, but average pooling maybe is more intuitive and results in less loss of information, if you like to think of it. All right, so this is the PyTorch documentation for maxpool 2D, which is what we'll be using in our convolutional neural network. As you can see, it takes as an input the kernel size. Whoops, can't get that. Kernel size, the stride, by default it's none, but you should put the size of the convolutional kernel. Padding, dilation, which are similar parameters to what we saw for nn.conv.2d. Cool. Again, there's a formula for what the output dimension is. Again, you don't need to know this formula by heart, but it's very helpful to look or to apply this formula between different layers of your CNN to understand the dimensionality and the number of learned features at every layer. When I upload the slides, you'll see that this link just points to the Torch documentation for the same. Cool. Let's go ahead and code our neural network. Actually, I'd encourage you guys to try it out first for a bit. For what it's worth, I hope that this structure, when we're calling super inside a class, is clear to you guys by now. Essentially, what super.init does is it initializes the class that we're inheriting from. So it initializes the module. Naturally, for every class, we try to have an init where we define variables, or in our case, our deep learning operators. And cool. So naturally, the first, so when we're writing nn.conv2d, we do in channels. In our case, this is fixed. Because we're dealing with an RGB image, we have just 3 input channels. Here, the out channels essentially represents the number of filters that we'll be using. As mentioned as a hint, let's use 32 out channels. Again, I'd like to point out that you should look at the in channels and out channels relation.
They're saying, could you speak like a little louder, maybe? I don't know what you can do, but they're saying they're having a little trouble hearing you on Zoom.
All right, cool.
It makes,
Sorry about that. I'll speak a little louder. But is there something you guys on Zoom missed until now that you'd like me to reiterate?
I'm wondering why the padding here is 1.
Essentially, this is like a design choice. We don't want to reduce the height and width dimension of our input features. So essentially, if we have padding 1, then we're going to have a layer of zeros around this input image, and thus the center of our kernel will actually sit at the top left. Right now, it's sitting a little bit inside the image, but if we have padding 1, then the center of our kernel sits exactly at the top left, and the output feature map will have the same height and width as the input feature map. But the number of channels will increase depending on the number of layers that we have. Sorry, the number of filters that we have. I hope that's clear.
Yeah.
Cool.
Can I ask a follow-up question to that?
Of course.
Uh, I'm sorry, I'm hearing myself. It's kind of annoying.
Uh, I'm not sure what I can do about that. I can maybe mute myself while you ask your question. Let's try
I
that.
think the mic that you are using, you could mute it. Yeah, cool. All right. So, yes. So just a follow-up question to what you just asked. Is what if I decide to use like for the padding, I decide to use the size of the kernel minus 1, so that means like 2. Would that be valid? And why wouldn't that be a better design choice? Because I think you mentioned you're using 1 for better design choice. But apparently I'm missing something out.
Cool. So nice question. First of all, it's good to question why we use a certain amount of padding. So in this case, as I said, padding usually can be a design choice, but in this case, we use padding 1 to retain the same output dimensionality of our feature map as our input. So currently, can't pause this. But if we have padding of 0, then our kernel sits exactly at the top left, and the center point of our kernel actually lies inside the feature map, not exactly at the corner. And as a result, that will result in a smaller output feature map than what we've given to it as an input. However, if we do padding 1, then the center of our kernel actually sits at the top leftmost pixel in our image. And that's why when we use a padding of 1, we'll get the same output feature map size as the input feature map size. However, if we were to use a padding of size 2, then the center of the kernel actually sits outside the image. And it will be looking mostly at zeros, assuming we do 0 padding. Uh, that's again not a very strong signal to the image, but who knows, depending on your task, it might be a valid design choice. At least for us, in the case of classifying images, padding of 1 is good enough. I hope that makes it better. I'll try to find a better illustration and maybe add it to the Piazza post for this lab.
So it
But
depends on the kernel size, right?
sorry.
I mean, the padding depends on the kernel size.
Yeah, absolutely. So it's the kernel size divided by 2, but the floor of that. So in this case, our kernel size is 3, but divided by 2, that's 1.5, and the floor of that would be 1. So that's why if we used a padding of 1, we'll get the same output size as we get the input size. Um, Naturally, if we used a kernel size of 5, then I'll have to do a padding of 2 pixels on the left, top, right, and bottom of the image.
Thank you.
No worries. Any other question or?
Yes, thank you for the clarification.
No worries.
Just just to confirm, doesn't mean that the bigger the bigger the pattern we add, the more information we lost, and vice versa. Does that make sense?
Uh, Sorry, could you repeat? You said when we add padding, we lose information?
Yeah, when you're explaining I grasp something, I'm not sure if it's right. So what I'm thinking is it true that the bigger the padding, the more information lost, and the lesser it is, the more information is retained?
So this, I would say you're sort of understanding, you're on the right track, but that's not exactly what padding does. Uh, we So while we are adding zeros to the edge of the image, we're not really losing information by doing that. We mostly just use padding as a way to make sure to have more control over the output dimension of our feature map. Uh, and yeah, it's not like if we don't use padding, we get more information. You could say we lose you could make the argument that we lose information because we're never truly sliding the center of the kernel across the entire image if we did no padding. Uh, but ultimately, I'd say that talking about information is not the right way to see padding. It's probably better to see it as a tool to have greater control over your output feature map size. And it's not strictly related to information.
Got it. Thank you.
No worries. Thanks for the question. Is there any other question online? All right, I'll carry on.
Oh, I have a question here. So
Of
in
course.
solution one, um, in the hint, it says use the ReLU activation, but here I didn't see you have implement that.
Oh, true. Fair enough. We could do that. There's actually, yeah, let's just do that. Thanks for pointing that out. Okay, so over here, once you filled out the basic convolution 2D kernels and added some pooling, you might look at this linear layer here. So as I said, in our architecture, we finally do have a linear layer which actually does the classification for us, because the output of a convolution kernel cannot really be classes, or cannot be like three distinct classes if I had three classes, or in our case, 10 classes. We need a linear layer for that. I hope everyone sees that. But we need to use a linear layer, we need to precisely know the number of the in dimension and the output dimension as well. Uh, so here, assuming we've all followed clearly using the kernel size of 3 and a stride of 1 and padding 1, the TAs have already filled out for you what the input to the linear layer should be, the input dimensionality. So assuming we've done all of this right, this should not throw an error, but let's find out. Actually, this might be 8 cross 8. Forgive me. Let's take a look. So I was saying this might be 8 cross 8, not 4 and 4. But let's find out. So I hope you can see what I'm doing here. What the way of stacking these functions mean is that I'm first doing a convolution on X, then I'm applying a pooling layer, and then I'm doing a ReLU after that. To someone's question, it's just a design choice where we choose to put the ReLU network, oh sorry, not the network, the ReLU activation. As the comments mentioned, we could define it here as well, but that's totally on you.
Well, I think there's a question in the chatting. Why we add the stride to layer 2?
Why we add stride where? Oh, sorry. Could you repeat the question, please?
Why we don't add the stride to layer 2? Convolution 2.
Oh, I think by default it takes in certain values, but sure, we can go ahead and add stride 1. Yeah, so I think by default it will fill in 1. I was just explicitly mentioning it there, but good question nonetheless. We can do the same thing here. Whoops. All right, awesome. I hope everyone's at this point now, and we've coded this neural network together while understanding where we're using what activation and what pooling layers we're using. Yeah, we can always print model. You can use CNN here. That essentially is our class that we've defined. We can print the model that just prints out the operations that we've used. Summary is from Torch summary. I think it's helpful because you can pass in your model and pass in an expected input size, and it will show you how that size changes through different layers of the network. And it also shows you the number of parameters through each layer of the network, so you can understand how big or small your neural network is.
Uh, Excuse me.
Of course. Yep.
Do we not have to add the softmax layer in the end, it, around the output layer?
That's a good question, and I did mention that. So we're actually going to be using cross entropy loss here. So if we go to what cross entropy loss is, I believe that this already takes as input logits. Yeah, it takes as input unnormalized logits for each class. So what this function does is it applies the softmax internally, and gives us output probabilities. I think there's another method where we can apply the softmax manually and use cross entropy loss with probabilities, or I think it's just the log loss directly over there. But in this case, because we're going to be using the cross entropy loss, as I also point out in our slides, we do not need to do a softmax, as the input is the unnormalized logits for each class. So as long as we have output dimension of 10, cross entropy loss will handle it for us. But good catch.
Yeah, thank you.
No worries.
Yeah.
Maybe I should have shown this earlier. I apologize for that. But as someone meant, sorry, is there a question online? Okay, cool. Again, just make sure you're passing in the right ordering of your input to the cross entropy loss function. So focus is there on mini batch, then your channels, and then the other dimensions that you might have for your input data. It's very important to make sure that the ordering is correct when using PyTorch functions. Okay, we'll quickly talk about the optimizer that we'll use. We'll be using Atom. I think you guys may be familiar with that. No need to worry too much about the other parameters. Most of them are initialized for you as default. We just need to pass in the params argument our model parameters. So let's go ahead and do that. Apologies for that. Okay, cool. So we were quickly talking about the optimizer of choice. We're going to use Atom. It's pretty much the best one out there. And it's also very good for image classification tasks. All right, I hope everyone's reached this part of the checkpoint and we have roughly the same number of parameters because we've defined the same network. All right, so before we get into actually writing our neural network, there are some points that I'd like to clarify. It's what you commonly see when writing a training loop in PyTorch. I just thought I'd quickly run through them. to help you guys understand what these mean because they're mostly implementation details. So the first part is setting your device. So when we set device is equal to torch.device CUDA if torch.CUDA dot is available, else CPU. Essentially, when we then use the device parameter everywhere else in our code, it'll put the tensors that we're using either on the GPU or keep them on the CPU. By now, you guys may know how advantageous it is to have all of these tensors on the GPU. Because you can quickly parallelize all of your computations. However, usually for smaller networks, like what we're training now, the actual cost of converting tensors from the CPU onto the GPU is much higher than the benefit you get by doing all of this processing on the GPU. Secondly, you'll see model.train. Again, this is not something, this is mostly an implementation detail. It sets dropout layers and batch norm layers to training is equal to true. So you actually have dropout during your forward passes, and for batch norm, you're finding the mean and standard deviation. A couple of other points that I'd like to bring your attention to is optimizer.zeroGrad and output. So optimizer.zeroGrad is really, really important because what PyTorch does by default is that it accumulates gradients throughout all of the mini batches. Sorry. Okay, sorry for that. I hope you guys can hear me again. So I was talking about the importance of optimizer.zeroGrad. It zeroes out accumulated gradients, and thus as a result, where we put it in our code is very important because we don't want the gradients that we've computed to be zeroed out just before our optimizer takes the step, which actually updates the parameters of the network. As we see here, loss.backward essentially does backpropagation and stores the gradients for every parameter inside inside a variable that's inside each parameter. And then optimizer.step, for us we've defined the optimizer to be Adam, that actually goes ahead and updates all of the parameters in our network. So essentially the number of times you're calling optimizer.step is the number of times the parameters of your network change. So broadly, this is the general structure or ordering of all of these components that we just saw. As I said, especially where you put zeroGrad is very important. We usually, or conventionally, we put it just before we take the output of the model. Then we have out is equal to model of batch. Then loss is the criterion. In our case, we've defined the cross entropy loss of out, comma, labels. That's what our model outputs and the ground truth labels. Then we do loss.backward, which computes all the gradients. And then we take an optimizer step. In addition to updating the parameters of the network, optimizer.step changes the schedule of our optimizer. So if you guys in your first homework used reduce LR on plateau or cosine annealing loss, it essentially changes the learning rate according to the scheduler. All right, cool. So I'm going to leave you guys with this. You guys should try writing up this network. I'll code it with you, but after that, my co-TA Ahmed will take over for understanding, interpreting results. This might take some time to run, so if you're able to code it out faster than I am, please go ahead.
Hi, Can you quickly share the parameter size? I just want to double check.
Of course. Do you have something similar?
Actually, it's 1/3 of that. I'm not sure why. Yeah, it's like 200,000, yeah, something. Yeah.
Uh,
Oh.
One thing I changed was this. Did you make this change as well? I
Oh,
think
okay.
the default notebook, it was 4 times 4.
Okay, I think yeah, I didn't change this. Okay.
Cool, yeah, sorry about that. I'll update the notebook after
Oh,
this.
yeah. Let me just.
I hope everyone's come to this stage where we've written the forward pass, computed loss, doing back propagation, and the optimizer step. Has the model finished training for any of you yet? Okay, cool.
In progress.
Yeah, can you see the screen?
Good morning, everyone. Welcome to the 2025 Fall CRP Rehearsal. My name is Fernando. Today I'm talking about the polymerization of vinyl polymers, as you can see from my title slide. This is probably my 8th CRP, and I'm more honored to open the day.
Okay, can you hear me?
Yes.
Yeah, that's better, Ahmed. Thank you.
Okay, so continuing on after we have seen how to train the model, we will first discuss some networks that has changed the image classification tasks. So starting from AlexNet, so AlexNet was one of the first networks that used CNN, that used convolutional layers, and it made a breakthrough in the classification task, especially in the at that time ImageNet classification task, and so it has surpassed the networks at that time by a large margin. And after that, a huge amount of proposed networks has been published and has made like the convolution neural networks based models has done a great deal in the image classification task. So one of the shortcomings of the networks that used AlexNet style is that when you put a lot of layers consecutively, we had an issue of the gradient vanishing. And so one of the solutions to that was using residual connections. So in this case, for ResNet, we had blocks of convolutional layers, and we connect the start of the block to the end of the block using residual connections, which we add the input of the block to the output generated by the block, and then we pass it on to the network. And that has added the capability of making deeper network, and also made us go further and increase the performance of convolutional layer space models or CNNs. So this is the list of the backbones that you will find on PyTorch. It will also help you during homework P2 later on. Please look at them, and I hope it will help you later on. Okay, so let's go to feature maps. When we trained those networks, we can see the activation of these networks against a different variety of inputs. So here we are seeing the activation map for an image of a cat as the network progress. We can see like the activation against the lines in the first blocks, and then as we progress, it will become more incoherent here. But if you look at the filters later on, you will see that the filters itself recognizes the patterns of the eyes or nose and so on, or even the face itself. And for now, we will just look at looking at the feature maps in the network in the notebook. So I'll pause sharing for now since I have I'll show you the other notebook. Okay, so here we in this checkpoint, you would see something like this. We already took for you the A sample image, and then we are generating the activation by defining a hook for the model, and then taking we register that hook to the first convolutional layer, and after we set the model to eval so that the model does not save the gradients, and also just for to make sure we use with torch .no gradients, and we input the sample image to the model, and since we have the hook that saves the activation to the dictionary, we just going to look at the dictionary and take the output, and we take the output from the GPU to the CPU and save it to the first layer activation variable. Here we are just looking at the number of filters by taking the shape. The channels in PyTorch are saved in the first dimension. So that's why we are taking the first dimension here. In other libraries that would that may be different, like that could be different. In TensorFlow, I believe it be the last layer, the last dimension. And here we are just plotting the image. You can execute that, but if you execute it, you will get something like this. For the first image, for the sample image. Yeah, for this image, I believe it's a rose. I'm not sure, but this would be the feature maps that you will get from the first convolutional layer. Okay, so going on, we also can do filters and weights visualization. Here we just like taking the filters defined by the model or by the training procedure of the model, and that helps us to understand what kind of patterns the model prioritize. So generally in the first convolutional layers, you'll get like a small, not a small, but basic features like lines. If the filter is large, maybe 11 by 11, you will see kind of curvature on the line. But if it's small, like 3 by 3 or 5 by 5, you will see lines, maybe diagonal lines, horizontal lines, and so on. And yeah, for example, here in the AlexNet, so AlexNet uses a filter of 11 by 11 in the first layer. If you look when the team who made AlexNet looked at the first filters, they have seen some these filters, which are mostly lines, vertical, horizontal, and diagonal. But there are some filters like this one, which is like a dot. And the filters, since they are taking the image, like the whole channels of the image, the filters can be also colored. So one of the filters is like orange with blue, and the dotted filter is green by purple, and so on. So in the second layer, the features gets more complex. So these may be like denser vertical patterns. There are some curvature in some of these images, and there is some like anti-diagonal patterns, and so on and so forth. And you also get some patterns like crosses or checkers, like some like the checkerboard patterns. But as you go on in the layers, you'll get more complex features. So the last layer of AlexNet has even the third layer of AlexNet has even like dog heads, circles and ellipses, and even blob patterns. And these are quite more complex than the first few layers where we only had lines or dots in them. And as you go on in the network, you'll get more complex features. Some of it like even had like human bodies and so on. And that is why in general, like the convolutional layers are really strong when in pattern recognition. And one of the strongest features of it that it does recognize this regardless of the position that these patterns appears at in the image. So going back to the network, this to visualize the the convolutional filters. Here we are doing it for the first layer, and we just take the weights from the model, the first layer. Here we call it conv1, and this is the weights of it. We convert it to NumPy. Here just for normalization, so that the colors are not oversaturated when we plot them. So we plot them filter by filter here, and if you run this cell, you will get, if you run this cell, you will get like the something like this. So since we are doing, since the first convolution layer has 3 by 3 filters, and this the plot would be generally like this, and here is like mostly simple filters or simple patterns. So yeah, so it's just like here a yellow line followed by some gradients from blue to purple and so on. Here is like blue line, yellow line, kinda. So it's just simple features, lines, diagonal lines, and as you stack the layers, as you look into, try to see the filters of other layers, and you'll get more complex features. So that would be it for the this lab. Do you have any questions, any suggestions?
Hello.
Yeah, I
I
can.
had a question. In the last part that you were showing, are these the weights? And I was confused between what is weights and features. Are they the same thing?
Oh, yeah. In this case, they are the same thing.
Oh,
The only difference
okay.
if you had biases, so that would be a weight but not a filter for the bias.
Okay.
But other than that, the convolution filters are weights in the end.
Okay. Thanks.
Yeah, welcome. Are there any more questions? Okay. Okay, I can stop sharing for now.
Yep. Okay, I think.
All right. Yeah. Thanks, Ahmed. I think we can end the session here. And if there are any questions in person, I'll happily take them now. Otherwise, thanks everyone for attending. And I hope you guys find this useful for your next homework and even in the future beyond that. Thank you.